Today is the last date for the application. So
yes.
I believe if you have not applied, you should apply.
Sure, sir.
Okay.
Thank you, sir.
Because the pattern of the exam is same. There's only a few changes. In CUET, you have a general test also, where is general aptitude, reasoning, all those questions will come. So we will train you for those things also. So just
Sure.
after completing this JEE syllabus, we will start the CUET exam. So keep all options in your hand. Even if you don't want to do BSc, just keep those options in your hand so that you, if something bad happens, like you didn't get your preferred college to JEE, and you will have option of CUET as well.
Yes, sir.
And as compared to JEE, it's much easier to score very well in CUET because you have plenty of time. It's on 22nd of May or maybe 24th May is CUET exam. It's easier. You have plenty of time. You can score very well.
Yes, sir. Thank you, sir. Yeah, I'll check on it.
Sure. So today's the last data.
Yes, sir.
Okay, so in the last class, we have finished this thing, dual nature thing. We discussed de Broglie hypothesis and all this. Is there any doubt in the yesterday's lecture? Adriel, Krishna, Pradarshini, Ashrit?
No, sir.
Okay. So did you practice questions on this dual nature de Broglie hypothesis, Pradarshini? No.
No, sir. I've been practicing thermodynamics more.
Okay, so from today onwards, at least start doing questions on this topic. Model physics. So photoelectric effect. For photoelectric effect, we will start with the concept of energy and intensity of radiation. See, radiation have dual characteristics. It behaves as a particle and it behaves as a wave also. So when we study experiments like photoelectric effect, we consider that radiation is behaving like a particle. For experiments like photoelectric effect, we consider radiation to behave like a particle. So we consider particle. And so when you consider light into the particle picture, there are few things which changes. So in wave picture, the energy will depend upon the intensity. Like if you have a bulb of 100 watt and you have a bulb of 1000 watt. So if you are considering light as a wave, then the energy from the 1000 watt bulb is greater than the energy of the 100 watt. But when you are considering light as a particle, energy have a different meaning, intensity have a different. We can explain photoelectric effect only if we consider light as a particle. If we consider light as a particle. So let's first see what does energy of radiation means when you consider light as a particle. Particle picture means you are considering light as photon. So in particle picture, energy is given by this expression. We discussed this yesterday also. It's hc by lambda, it's h. So when you consider light as a particle, this is the expression of energy. So energy depends upon frequency, energy depends upon wave. Energy is independent of the power of it. You can say that energy is independent of the power. Power. Which means it depends upon wavelength and frequency. So if I give you two bulbs, I give you one bulb of 100 watt, and this bulb is of red color, and I gave you another bulb. This bulb is also of 100 watt, not 100 watt, 1000 watt, but of red color. Now, since the radiation, the wavelength of the light coming from both the bulb is same, so it does not matter what wattage you have, the light coming from both the bulbs will have same wavelength, so they will have same. from both the bulbs, light waves will have same. So that is the difference between the wave picture and the particle. When you consider light into particle picture, then energy depends only on frequency and wavelength. But when you consider this into the wave picture, then energy will depend upon the intensity, it will depend upon the power. So if you are considering your light as a wave, then 100-watt and 1000-watt bulb both will have different effects. Next is intensity. In particle picture, so when you are considering light as a stream of fast moving particles, in particle picture, intensity simply means number of photons per unit area per unit time. So this is intensity. So in particle picture, intensity means number of photons per unit area per unit. So when I say that I'm increasing the intensity of the radiation, that means I'm saying that I'm increasing the number of photons. When I say that I'm changing the energy, that means I'm changing the frequency or I'm changing the wavelength. And remember one thing, intensity and energy are two different. They're totally two different. Marita, I have to discuss few things with you. So please stay in the classroom after the class.
Okay, sir.
So intensity in particle picture, intensity means just number of photons per unit area. So these are the two things that should be very, very clear. If I'm changing frequency, then I'm changing energy, not the intensity. If I'm changing intensity, that means I'm changing the number of. So if I take a 100-watt bulb, and a 200-watt bulb, and both bulbs are of red color. So Ashrit, both the bulbs will have same energy or different energy? The radiation coming from both the bulbs will have same energy or different energy?
Different, sir.
Same energy. Since the color is same, that means frequency is same and energy depends upon frequency. Yeah?
Yes.
Energy depends on frequency. What about the intensity? See, from 200-watt bulb, the intensity of light is more. That means this 200-watt bulb will emit more photons as compared to the 100-watt. This is what we mean by intensity. Greater the wattage, greater the intensity, means greater would be the number of photons which are emitted by this. After intensity, let's see what is work function. See, what does work function means? Work function means number of photons, not just number. So if you have an atom, this is the nucleus, which is positively charged. Around the nucleus, you have electrons. This electron is bounded with the nucleus due to electric fields. If you want to remove this electron, you have to apply something. And if this atom is from the top surface of a metal, then the energy required to remove this electron is what? So minimum energy required to remove it. So minimum energy required to remove it. So when we talk about work function, we are talking about metal surface. So that's what. We will be representing it by pi. This is how we represent work. After work function, the next is, now you can understand what does photoelectric emission. photoelectric emission. Just note it down when you start with photoelectric emission. Say in photoelectric effect, you will get many graphs. To choose the correct graph, this difference between energy and intensity should be very. Tell me once you have written. Krishna, Marta.
Done, sir.
Done, sir.
So are you able to solve questions from thermodynamics and KTG?
Yes,
Most
sir.
have tried. Marta, were you able to solve all questions on thermodynamics and KTG from PY?
Yes, sir, the homework I was, but not always.
But after taking hint from the solution, are you able to solve those questions?
Yes, sir.
Or this should not be the case that even after seeing the solution or even after taking the hint, you are not able to solve that. Ashit, you have to solve questions from JEE PYQ and NEET PYQ. Someone from the operations team must have shared 2 books with you, NEET PYQ and JEE PYQ. Did they share those books with you? Soft
Not
copy?
yet. I guess not yet, sir.
Okay, I'm asking them to share.
Just.
To share. And just one more thing. See, in crash course now we don't have so much time for mock. I can have that time, but you don't have that time. So after the class, don't invest your time in any type of mock tests. That won't be very beneficial for you. See, if the one thing should be very clear in mind that in JEE, questions does not repeat from mock test series of any attempt. The questions, if they are getting repeated, they will get repeated from NCERT or JEE. So whatever time you have, invest that time into JEE PYQ, and if you left with some time, invest that in NCERT questions. Today I'll be sharing class 12th NCERT solutions with you. The list of very important questions of NCERT, some tough questions from NCERT that can come in. I've shared that list also in for your class 12th exam, but since they are students, I'll share that list. So whatever time you have, invest that time into JEE PYQ. Because if you practice from various sources, you won't be able to cover your targets. Okay. Okay, after work function, next is photoelectric emission. Simple experiment on photoelectric emission. So photoelectric emission means if you want to emit electrons from the top surface of a metal, you need to supply some energy. And energy equal to work function. If you're supplying that energy in the form of photons, like if the energy of photon is providing the energy equal to work function, then the emission is known as photoelectric emission. If you provide that energy through thermal energy, then you call it thermionic emission. If you provide that energy through some fast moving electrons, then you will call it as secondary emission, but we have to concentrate on photoelectric emission. So I'm doing a thought experiment. Whatever we do in today's class will be based on this experiment. So this is a metal plate. This is a metal plate. These are various electrons. This is one electron of the metal plate. The work function of this electron is 2 electrons. That means if you want to eject this electron from the metal plate, you have to supply an energy of 2 electrons. Now let's say I incident some photon. The energy of the photon is 1 electron. So see, energy of photon is less than work function. E is less than work function. That means this photon cannot eject electrons from the metal surface. So no photoelectric emission. I will write photoelectric emission as PE. So no photoelectric emission. Now, same electron of the metal surface. I incident a photon of energy 2 electron. And the work function is same, 2 electron volt work function. So your energy is now equal to the work function. Energy of photon is equal to work. So yes, electrons can eject, so photoelectric emission will take place. But these electrons will just come out of the metal surface and come at rest. These electrons cannot move. You're not supplying that much of energy so that these electrons can. The electrons will come out of the metal surface and will stay. You can say that kinetic energy of the electrons will be zero. If you want electrons to have some kinetic energy, that means you have to incident photons having energy greater than the work function. So say you incident a photon having energy of 4 electrons. Work function is again 2 electrons. So you're supplying greater energy as compared to work function. Your energy is more than work function. That means photoelectric emission will take place. And the extra energy will go in the form of kinetic energy. So you incident a photon of 4 electron volt. Energy required to eject electrons is 2 electron volt. So the kinetic energy will be 4 minus 2. That will be 2 electron volt. Next, this is electron. Work function is same, 2 electron volt. You incident 2 photons, each of 1 electron. Now this is something that you should understand. 2 electrons of 1 electron volt. Work function is same, 2 electrons. So this one single electron have energy less than the work function. So this one photon have energy which is less than the work function. Have 1 electron volt energy and the work function is 2 electrons. So this photon cannot emit electrons. Because to emit electron, the energy should be at least equal to work function. But what if I incident 2 photons? Both have energy of 1 electron volt. If I add the energy of two photons, the total energy will become 2 electrons. But these 2 photons can never simultaneously collide with this electron. The size of electrons and photons are such that at one instant of time, only 1 photon and 1 electron can collide. 2 photons cannot simultaneously collide with an electron. So there is no point in adding the energy of 2 photons because they are not colliding with the electron at the same time. So here again, energy will be less than the work function. Again, no photoelectric emission. So from here, you can say that on increasing the number of photons, energy will not increase. So you can remember this in this way. So 1 electron, 1 photon. Means 1 electron can collide with 1 photon. 2 photons cannot collide with 1 electron. You can take one more case, like you take 1 photon. This photon have an energy of, let's say, 6 electrons. And this is the electron. Work function is same, it's 2 electrons. So this photon has sufficient energy to eject 3 electrons. But again, the issue of cross-section. The size of electron or photon are such that at one time, 1 photon can collide with only 1 electron. this photon cannot collide with 3 electrons. Although this has sufficient energy to eject 3 electrons, this have an energy of 6 electrons, and the energy to eject 1 photon is 2 electrons. But the problem is 1 photon can collide with 1 electron. So only 1 electron will eject. Only 1 electron will eject. And the rest of the energy will go in the form of kinetic energy. 6 minus 2, so that is 4 electrons. So this important conclusion is on increasing energy of photon, on increasing all these statements that I am writing here, I'll be using all these in graphs. On increasing energy of photon, kinetic energy of electron will increase. Kinetic energy of electron will increase. Not the number of electrons. Number of electrons will not increase, only the kinetic energy of electrons. If you want to eject, instead of 1, if I ask you to eject 4 electrons, I want to eject 4 electrons, then what will you do? Instead of 1 photon, now you will incident 4 photons. 1 photon can eject only 1 electron. If you want to eject 4 electrons, you have to incident. So instead of 1, I am incidenting 4 photons. So what I am changing? I am changing the energy of photon, or I am changing the intensity? Yes. It's an open question to all of you. Intensity. You know, intensity is number of photons. Earlier I was incidenting 1 photon. Now I'm incidenting 4 photons. That means I'm increasing the number of photons. So number of photons is increasing. That means intensity is. So if you increase intensity, on increasing intensity, number of electrons will increase. And this number of electrons is current. Current is nothing but flow of charge. Now, more the number of electrons, more will be the current. Note it down. This is entire photoelectric emission. If you understand these 5 fixed cases, that means now you know photoelectric emission. Just have to draw a graph and write some basic equation. Entire photoelectric emission is this. Note it down. Yes, can I change the slide now?
Once again, sir.
Please apply for CUT. Today is the last date if you haven't applied yet. Today is the last date for the application of CUT. The syllabus matched with that of this JEE. There are few new topics that can be discussed in 1 or 2. Even if you're not planning for BSc, keep options in your hand. Maida, did you apply for CUT?
No, sir.
Discuss with your parents today is the last date. Just apply for that.
Okay, sir.
So there are many colleges in India which will ask you for CUT score. So you should have two scores in your hand. One is JEE score and another is CUT score. Can I change the slide now?
Yes, sir.
Okay. After photoelectric emission, let's start with this thing. Hertz experiment. Now we will just draw a graph. Whatever we study in the last section, we will again do that thing in the form of Hertz experiment. See what Hertz did. Hertz took an evacuated tube. This is a tube, evacuated tube. So evacuated tube means this tube have vacuum. There's no gas within the tube. Then he connected this tube with a cell. And these are two plates. One is negatively charged and another is positive. Since there is no medium inside the tube, so these electrons cannot travel from one point to another. There's nothing that can travel from here to it. There's no medium, no electron, nothing. So no, there will be no current here. If I connect an emitter here, there is no current. Which is very obvious. Current is the flow of charge. For current, you should have electron. For electron, you should have medium. There is no medium within the tube. Next, what he did, he incident some photons. So when he incident some photons, these photons strike with the plate and it ejects some electrons. And these ejected electrons start moving towards the another plate. So when these electrons reach the another plate, the circuit gets completed and you start getting some reading in the emitter. So what is happening here is a photoelectric emission simple. The energy of the photon is greater than the work function of the plates, due to which the electrons get ejected and electrons will move towards another plate. And due to the movement of electron, there is current, and this emitter is reading that current. That's the simple Hertz experiment. On the basis of this Hertz experiment, Hertz plot two graphs. On the y-axis, he took current in milliampere. On x-axis, he takes frequency, Hertz, the frequency of radiation. So if I increase the frequency of radiation, that means I'm increasing the energy of the photon. Energy of the photon is H. On increasing energy of photon, kinetic energy of electrons will increase, not the number of electrons. So when you increase frequency, then current will not change. I'm repeating again. If you increase the frequency of photon, energy of photon will increase, kinetic energy of photon will increase, but the number of photons will not change. Current is related to number of photons. So on increasing frequency, number of photons is not changing. Graph will be straight. But if I take intensity on x-axis, and current on y-axis, which is in milliampere, and if I increase intensity, that current will increase. It will increase linearly. The reason is if I increase intensity, that means I'm increasing the number of photons. So on increasing number of photons, the number of ejected electrons will increase. And that eventually increase the current. That will change the current. So current. So these are two important graphs. Just draw these graphs, then we'll do variation with potential. On the same sheet, we'll do variation. Is it clear? These two graphs, Rehan, Krishna, Pradeshini?
Yes, sir. Yes, sir.
Photoelectric effect is a very small and a very scoring topic. Just 4 or 5 graphs and three equations, 3 or 4 equations. Right?
Done, sir.
Okay. So after Hertz experiment, now we will see the variation of this current with respect to potential. We will see the effect of potential on current. So to see the effect of potential, I will draw a rough table. That table will help you to plot graphs. So let's say you incident 100 photons on this plate, and energy of each photon is greater than work function. That means each photon will emit 1 electron. So if you incident 100 photons, that means 100 electrons will get ejected. So I write number of ejected electrons. Initially, that number is 100. Then this is the potential V, and I write potential. Then we will take number of electrons which are reaching the plate, because only those electrons will contribute to current which read the opposite. So electrons reaching plate 2. So we are considering only those electrons which are reaching plate. So 100 electrons gets ejected out. When these 100 electrons gets ejected from here, they all should reach the second plate. But what happens is when these electrons get ejected, majority of them gets lost. The electrons can collide with the wall of the container, or they can collide with each other. So the majority of electrons get. So when you did not apply any potential, you apply zero potential, 100 get ejected and only 10% electrons reach the. So the current will be corresponding to 10 electrons. So how the electron gets lost? They collide with each other, they collide with the wall of the container, and they lose. Next, again, you incident 100 photons, 100 electrons will eject. But now you apply some positive potential here. Let's say you apply a potential of +5. This positive potential will attract electrons. Due to attraction, more electrons will reach. So let's say 30 electrons. So it's due to this positive. If I increase the positive potential from +5 volt, if I make it 10 volt, then more electrons will reach here, and a time will come when all 100 electrons will reach. 100 electrons will eject and 100 will. So this corresponds to saturation. Means if I increase potential further, instead of +10, if I give +20, then again these will be 100, because the number of electrons which are ejecting is 100. This will not change due to this. So always 100 electrons are ejecting. If you apply a very high potential, then all electrons are reaching the plate. That means saturation happens. Your current is saturated now. On increasing potential, your current will not increase. But instead of positive potential, let's say 100 electrons gets ejected. Here, instead of positive potential, you apply a negative potential. You apply a negative potential. So what will happen? This negative potential will repel electrons. It will not attract electrons. This negative potential will repel electrons. So let's say you apply a potential of -5. So this -5 volt will repel electrons. So without potential, like when you applied 0 volt, 10 electrons were reaching. Now not even 10 electrons, let's say 3 electrons are reaching. So current will decrease. If you increase the negative potential, let's say you make it -8 volt. And if this potential is sufficient to provide a repulsive force which can repel all electrons. See, these electrons are moving in this direction. If you apply a sufficiently strong negative potential, then this negative potential can repel these electrons. So there is no electron which is reaching. No electron is reaching. And this potential is what we call stopping potential. This is what we call stopping potential. There's one more name, it's also known as cutoff potential. So cutoff potential means potential at which your photoelectric current reduced. What happens at stopping potential? At stopping potential, your plates have sufficient repulsive energy to repel the electrons. So you can say that at stopping potential, the kinetic energy of electrons is equal to repulsive energy. How we calculate energy? Electronic charge multiplied by the potential. V naught is the stopping. So this is the relation between kinetic energy and stopping. Where kinetic energy is charge multiplied by stopping. Now you can plot a graph between x on x-axis. You can take potential volt. On y-axis you can take current. Your current is in milliampere. So when your potential is 0, few electrons are reaching the second plate. So current is not 0, it's non-zero. When you increase positive potential, current will increase and slowly it gets saturated. But when this is 0 volt. But when potential becomes negative, the current will start decreasing, and at a particular potential, current will become 0. So this potential is your stop. Potential at which current reduces. From negative, it's saturated to a fixed value. So this is the graph between current and potential. That's stopping potential, and this graph also shows the effect of potential. If you increase positive potential, that your current will increase, but eventually it gets flatter, it gets saturated. This here is the saturation. Is it clear, this discussion? Saturation current, stopping potential, and effect of potential on current. Hamza, Adriel, Ashrit.
Yes, sir.
Yes, sir.
Show it. Note it down.
None, sir.
Hamza, written.
Just a minute, sir. Done, sir.
I'm changing the slider. Pradarshini, Krishna, written.
Done, sir.
Yes, sir.
Now, this saturation current will depend on the intensity of light. So if you increase intensity, that means you are increasing the number of photons, number of electrons will increase. It depends upon intensity. It does not depend upon frequency. So remember this. Your saturation current will not change with frequency. The next is stopping potential. The next is the stopping potential. Stopping potential depends upon frequency. Because stopping potential depends upon kinetic energy of electron. And kinetic energy depends upon frequency. This does not depends upon intensity. So from here, you can draw two types of graph. Like there's one question, this is potential in volt, and this is your current in milliampere. I ask you to, let's draw it on another picture. It can ask you to draw this graph, the same graph, potential in volt and current in milliampere. But the condition is you have to draw for 2, 3 or 3 different radiations. Radiations having same frequency. Different intensity. Now you have to think. Same frequency means stopping potential will remain same or saturation current will remain same. See, saturation current depends upon intensity and stopping potential depends upon frequency. So if frequency is same, that means for all 3 radiations, stopping potential will remain same. You are changing intensity, saturation current depends upon intensity, so saturation current will change. So if you draw a graph, the graph will look like this. This is for first one. For second radiation also, see, this will not change. Stopping potential will remain same. Only the saturation current will change. Only the saturation current will change, nothing else. For all 3, your stopping potential is same. Stopping potential is not changing. This is for first frequency in new one. This is for second, sorry, frequency is same, intensity. This is for the first intensity I1. This is for the second intensity I2. This is for the third intensity I3. Say here, saturation is maximum. So we'll say that I3 is greater than I2, which is greater than I. The same frequency and different intensities. Yes, Ashrit, stopping potential does not depend upon intensity. That's why for different intensities, you're getting the same stopping point, the same point. But saturation current is. If I ask you to draw the same graph, this is potential in volt, current in milliampere. But now the condition is same intensity, and different frequency. Same intensity and different frequency. So same intensity means saturation current will be same. Different frequency means stopping potential will be different. So this is the graph for the first. Stop. If you increase the frequency, stopping potential will increase, but saturation current. If you do it for third frequency, stopping potential will increase, but saturation current will increase. So for all 3 graphs, the frequency is different, D1, 3. You have different stopping potential, minus V01, minus V02, minus V03. So your U3 is greater than U2 is greater than. Okay, yes, no reason. So that was about graph. Now we'll do Einstein's photoelectric. So saturation current depends upon intensity of light and independent of light. Stopping potential depends upon frequency, it's independent of it. So I1, I2, I3 are intensities. Nu1, Nu2, Nu3 are frequencies. Nu3 is the maximum frequency. That's why stopping potential is more negative. After this, we have Einstein's photoelectric equation. Einstein's photoelectric equation. So this is Einstein's photoelectric equation. Like if you have a metal surface, this is your electron. Work function of the electron is phi naught, its work function. And you incident a photon, energy of the photon is E. E is the energy of photon. This, if energy of photon is greater than work function, then this electron will eject with a kinetic energy K. So Einstein's photoelectric equation basically connect these three things: energy, kinetic energy, and work function. This is the same thing from where we have started, that kinetic energy is energy of incident photons minus work function. This simple equation is known as Einstein's photoelectric equation. Now you can convert this equation into many forms. Like the first variation is you can play with energy. You can write your energy is h nu, so it will be h nu minus phi naught. So energy is h nu now. What is nu? Nu is frequency of radiation. This is the frequency of incident radiation. Frequency of radiation. You can even write this as Ke is hc by lambda. This we did yesterday also. It's hc by lambda minus pi. So this lambda here is wavelength of incident radiation. The main equation is equation number 1. Now you can keep on converting it into many forms. So you can do one more thing. We know that kinetic energy is E V naught, where V naught is stopping potential. So if I call this as equation number 4, and you can substitute this 4 into 2. So when you substitute 4 into 2, you get E V naught is equal to h nu minus phi. This is again one equation. You may need this equation in some cases. This is equation number 3. Not 3, sorry, 5. You can do one more thing, like this work function phi naught. This can be written as h nu naught, or this can be written as hc by lambda naught. This nu naught here means threshold frequency. Means the minimum frequency for which electrons will get emitted. This is threshold frequency. Along with threshold frequency, you should remember this is the minimum frequency of radiation. This lambda naught is the threshold wavelength. Threshold wavelength. And threshold wavelength is the maximum wavelength. Frequency and wavelength are inversely proportional. See, nu is equal to c by lambda. So nu and frequency are inversely proportional. That means if frequency is increasing, then wavelength will decrease. If frequency is minimum, that means wavelength will be maximum. Next, what you can do is you can, in this equation here, Instead of phi naught, you can write h nu naught. Here, instead of phi naught, you can write hc by lambda naught. So the expression will become Ke is h nu minus h nu naught. Ke is hc by lambda minus hc by lambda. So these are the different forms of Einstein photoelectric equation. Note it down, then we will plot graphs and we'll do numericals based on this equation. So numericals on photoelectric effect will come on these equations only, these 6-7 equations which are written. Einstein got the Nobel Prize for this equation, Einstein's photoelectric equation.
Sir, can you show the graphs above again? I got disconnected when you were telling to write it down.
Okay, first write this thing, then I'll go back to the page. Just note it down, I'll go back to the previous slide. Yeah, everyone have written up to here? Hamza, Rayan,
Yes, sir.
so this graph you're talking about?
Yes, sir. I'll just take a screenshot. I'll write it later. Done, sir. Done, sir.
Okay. So the first question is plot kinetic energy versus frequency. So this is the relation between kinetic energy and frequency. Kinetic energy is h nu minus phi. So this equation, these are the two variables. Kinetic energy and frequency are variable. If you equate it with the equation of straight line, y is mx plus c, they can identify, okay, instead of slope, you're getting h, instead of y-intercept, you're getting minus phi. So if you plot this graph, this is on x-axis, I'm taking frequency, which is in hertz. On y-axis, I'm taking just kinetic energy. Graph will be a straight line. But graph will start from threshold frequency. Because if frequency is less than threshold frequency, that means there is no emission. So graph will start from here, it will go straight. If you extraplot it, it will cut the y-axis here. And this y-intercept is nothing but your phi naught, minus phi naught. And the slope of this graph is nothing but h. If angle is theta, then slope is tan theta, right? and h is the Planck constant. So that means the slope of this graph is constant. You take any material, the value of Planck constant is not changing. Means if I give you one more metal, like I give you iron, then I give you copper, and I ask you to plot the graph, you know that graph will be a straight line. Graph can have different intercept because this is work function. Work function is different for different metals. But for all metals, the slope will give h Planck constant. Planck constant is not changing. So if you take another metal, everything will get changed except the slope. See, y-intercept is changing, but slope is not changing. Means again, if you do tan theta 2, it will be equal to h. So if you draw kinetic energy versus frequency graph for all metals, work function will be different. The graph will start from different positions, but will have same angle, will have same slope because slope is connected to the this thing, your Planck constant. There can be a similar graph. It can ask you to plot stopping potential versus frequency. So for this particular graph, stopping potential versus frequency graph, you can use this equation EV naught. Instead of kinetic energy, we can write EV naught is h nu minus alpha. So from here, you can write this as V naught is, you can take e to the right hand side, it's h by E nu minus phi naught divided by. So when you compare it with this equation, y is mx plus c. Instead of m, you are using h by e. So your slope is h by e. Y-intercept is minus of phi naught. So since the linear equation, so graph will again be a straight line. So this is frequency in hertz. On y-axis, we have V naught. Graph will start from threshold frequency. Because if frequency is less than threshold frequency, then there is no photoelectric emission. And just like the previous case, your graph will be a straight line. But now when you calculate slope, slope will be tan theta. And tan theta is equal to, slope is h by e now. Y-intercept is this. This is minus of phi naught divided by, this is the y-intercept. So these are two important graphs, just note it down. Now see the type of numericals that you can get on photoelectric. So this is important. For this graph, slope will not change. For all metals, slope will be same because slope is equal to Planck constant. Planck constant is not changing. But y-intercept would be different. Different metals will have different work functions. So y-intercept would be different. Okay. Next, let's start with the variables. So, see, the easier numerical will be using just Einstein photoelectric equation. More involved numericals will connect this. One second. Involved numericals will connect it with yeah, sorry. So more involved numericals will connect photoelectric effect with mechanics. In photoelectric effect, the kinetic energy term that you have that can be connected to mechanics, that can be connected to energy conservation, that can be connected to momentum conservation. Similarly, through that kinetic energy term, questions can be connected to magnetics also, the radius of charged particle in magnetic field, circular path, elliptical path, and those. So first do a question which is based only on this thing, photoelectric effect. So radiation of wavelength lambda is incident on a metallic surface. The stopping potential of ejected photoelectrons is 4.8. So stopping potential is mentioned. That means we'll be using this equation. EV naught is h nu minus phi naught. Now wavelength is given, not frequencies. We're using this one. hc by lambda minus. So initially the wavelength is lambda. Stopping potential is 4.8. So it's E. Instead of V naught, you can write 4.8. This is hc divided by lambda minus of pi. This is first. If the same surface is illuminated by radiation of double the previous wavelength, then the stopping potential becomes 1.6. And is asking the threshold wavelength. Threshold wavelength means you should write your phi naught in terms of threshold wavelength, which is hc by lambda. So instead of phi naught, I should write hc by lambda, asking about the threshold. Now, if the same surface is illuminated by radiation of double the previous wavelength, the stopping potential becomes 1.6. Instead of V naught, you will be writing 1.6. Instead of lambda is double. Means instead of lambda, you will be using 2 lambda. Adriel, will there be any change in the threshold wavelength, or threshold wavelength will remain same?
Same.
Yeah. So you should write somewhere threshold wavelength, threshold frequency, and work function. That depends upon the nature of material. So if you have a copper plate, its threshold wavelength, threshold frequency, and work function are same. It will not change. You can keep on changing the wavelength of light. See, earlier you incidented wave law of 5,000 angstrom. Then you incident a wave of 6,000. Then you incident a wave of 7,000. You are changing the wavelength of the wave. But stopping potential will not. This work function is not changing. Threshold wavelength will not change. Threshold frequency will not change unless you change the metal. Say earlier you have copper, then you take iron. Now work function will change. Threshold wavelength will change. Threshold frequency. If material is same, then threshold will not. So it will be minus of hc by lambda naught. This is the equation. From these two equations, you are supposed to calculate this lambda naught. So I believe if I divide them, if we divide these two equations, then E will get cancelled off with E. 16 will get 1.63 is 4.8. HC will get cancelled out. And we are left with 3 by 1 is 1 by lambda minus 1 by lambda naught divided by 1 by 2 lambda minus 1 by lambda. Now you can cross multiply them. So cross multiplying means this is 3 into 1 by 2 lambda minus 1 by lambda naught is equal to 1 by lambda minus 1 by lambda. So 3 by 2 lambda and 1 by this is 3 by 2 lambda. You can take this lambda naught to the left hand side, minus 1 by lambda. This minus 3 by lambda naught, so it will be 3 by lambda naught when it comes to right side minus 1. So this will be 1 by 2 lambda. And this is 2 by lambda. So you can say that lambda naught is 4 lambda. So this is the correct. So this is one type of question on photoelectric effect. In these type of questions, you won't be using any step outside Einstein photoelectric. All steps will include Einstein photoelectric. Then we'll do another type of question which will connect photoelectric effect equation with either mechanics or with magnetics. In mechanics, it will connect it with conservation of energy and conservation of momentum. Magnetics, it usually connect with the path of charged particles, circular path of charge. Note it down, then we'll do the next type. Tell me once you have written, we'll do the next question.
Done, sir.
Done, sir.
So the next question will connect photoelectric effect and magnetics. So read this question, at least write few steps. Would be good if you can solve the entire question. I'm giving you 2 minutes. Just read the question, write the given terms. Make a strategy, write the relations that we'll be using here. Okay, I believe you have at least noted down the given terms and the relations that you'll be using. See, what is given? Wavelength is given. Work function is given. And magnetic field, let's ignore magnetic field for the time being. Maximum kinetic energy. So what is happening here? This is a metal surface. This is electron. You incident photons on these electrons. Energy is greater than the work function, so these electrons get ejected with some kinetic. Now, this electron is placed in a magnetic field, which is perpendicular magnetic. So if electrons move in a magnetic field which are perpendicular to it, then the path of electron will be circular, complete circle, semicircular arc. The radius of that circular path is given by this expression. It's mv divided by q. And this question is asking the magnetic field. So from here, you can say that magnetic field will be its mv divided by qr. So see, m is given, mass of electron, charge is given, radius of the path is given, velocity is unknown. What is v? V is the velocity of this electron which is coming. So to calculate the velocity of electron, you need kinetic energy of electron. So to need kinetic energy of electron, you need photoelectric effect equation. So this is how he is relating magnetics with the photoelectric. So first you can calculate, you know that you need velocity only. For velocity, you can write this equation. Kinetic energy's wavelength is given, so it's hc by lambda. Work function is given 1.25. Now there is one point. See, you have to do your calculations in SI unit because this is in meter. Your magnetic field will be in Tesla. So no need to convert this into electron volt. So you convert this electron volt into joules. It will be 1.6 into 10 raised power minus 9. See, this is the work function. Huh? This is the work function. 1.25 electron volt. You can't keep electron volt. You have to convert this in joules. So just multiply it with 1.6 into 10 raised power minus 9. HC is given in the question. Say this is 20 into 10 raised power minus 6. 20 into 10 raised to the power minus 26. Wavelength is 500 nanometer. So 500 into 10 raised to the power minus 1.25 into 1.6 into 10 raised to the power minus. So this 0 will cancel this 0. This kinetic energy will be 2 by 25 or 1 by 25. 10 raised to the power minus 26 plus 9, it's around minus 16. Not minus 16, minus 70. Minus 1.25 into 1.6 into 10 raised to the power minus. Now let's solve it. 1 by 25, how much is 1 by 25? It's 0.04, right? 1 by 25 is 0.04 into 10 raised to the power minus 17 minus this stuff 1.25 into 1.6. 1.25 into 1.25 into 1. So it's 2 into 10 raised to the power minus 9. So if I solve it here, it's 0.04 now, means 4 into 10 raised to power minus 2, means this is 4 into 10 raised to the power minus 19 minus 2 into 10 raised to the power minus 9. So it comes out to be 2 into 10 raised to the power minus 9. So you have kinetic energy. If you have kinetic energy, you can calculate velocity. It's half mv square is 2 into 10 raised to the power minus. So from here, you can calculate the velocity, and then velocity can be substituted. So these are some good questions on photoelectric emission, where they connect photoelectric emission with the other topics. Not enough. So I'm not doing the last calculation, right? To just waste my time. You can do something else. Similarly, like here it gives magnetic field, so it connected with magnetics. It can be connected with conservation of momentum, collision. It can be connected to de Broglie hypothesis. This kinetic energy can be used to calculate the wavelength of electrons. Now, if you solve questions on photoelectric emission, you will get all those scenarios which I'm talking about. You will find questions where using this kinetic energy asks you to calculate a wavelength of electron. So that is photoelectric emission plus de Broglie hypothesis. Haji, written?
Yes, sir.
Okay. So that was about this photoelectric emission. After photoelectric emission, we'll start atomic structure. So atomic structure. Shit, I'm not sure. There must be, since all central universities take this test, so there should be. But I'm not very sure. You will get this thing when you are applying. When you're applying for CUET, you will. This information should be there in the form. Okay, next is atomic structure. So atomic structure, it starts from the Dalton model. Then there is J.J. Thomson, then there is Rutherford, then Bohr's model. The questions that you get in your exams are from Bohr model. So I'm not discussing Dalton, J.J. Thomson, and Rutherford. I'm sharing a PDF notes. That PDF have information of Rutherford, J.J. Thomson, and Dalton models, but they're not required. You should the questions that come in your exams are from the Bohr model. So we will discuss Bohr model. Bohr's model. This is again a very scoring topic. Like within 2.5 hours, you can prepare this topic, atomic structure, and you can be confident that if a question comes, you'll be able to attempt it. An easy and very scoring. Bohr's model. So Bohr's model has some postulates. The first postulate is in an atom, if this is the nucleus, then electrons revolve in certain fixed orbits, and those orbits are also known as shapes. An important thing about the orbit is when electrons are revolving in a particular orbit, they will neither gain nor will lose energy. Usually what happens, if an electron is going in a circular path, then the direction of its velocity is changing. Due to change in direction of velocity, it will emit radiation. Its energy will decrease. This is what happens in classical world. If you take a charge particle and somehow you make that charge particle to move in a circular route, that charge particle will emit some energy. It will lose energy. But atom is something very special. If electron is revolving in an atom in orbits or in shell, then it will neither gain nor it will lose energy. This is something which is very new, which does not happen in our macroscopic world. This happens within the atom. But if you come to macroscopic world, energy will decrease. If you take an electron and you start revolving that electron around this pen, then the energy of electron will gradually decrease. But within the atom is something very special. Microscopic level physics is very different. Electron will not lose any energy. And those special paths where electron can revolve without any loss or gain of energy are known as orbits or shells. The name of the shells are written as K. The second postulate of the Bohr's model was, in these shells, the angular momentum is quantized. The angular momentum of electrons. Angular momentum of electrons is quantized. Angular momentum is quantized. Quantized means angular momentum will have fixed value. Now, what is the expression of angular momentum? It's mvr. Quantized means it's nh by 2. H is Planck constant, 2 pi is constant, n is number of orbit, 1, 2, 3. So the first postulate says that electron can revolve in certain special orbits where its energy will not decrease, it will not lose energy. And the second one says that in those orbits, the angular momentum of the electron is quantized. Third postulate says okay, the second postulate, in angular momentum, mvr, is an integral multiple of nh by 2. This is the second postulate. N will start from 1, it's 2, it's 3, and it's 4. Third postulate says different orbits have different energy. Energy of electron is fixed within a particular orbit. Like first orbit, energy is fixed. In second orbit, energy is fixed. But if electron jump from one orbit to another, means if electron shifts from orbit number n1 to orbit number n2, it shifts from here to here. So if it is jumping from an orbit having low energy to an orbit having high energy, this electron will absorb energy. And if it is jumping from high to low energy orbit, then this electron will emit energy. So if electron jump from low energy to high energy orbit, it will absorb energy. If it jumps from high to low energy, it will emit energy. And it emits energy in the form of radiation. So these are the three postulates of Bohr. On these postulates, the whole model of Bohr is based. See, in all these three postulates, there is no discussion of electron-electron interaction, which means you can use Bohr model only if you have a single electron. But if you have an atom which have multiple electrons, Bohr model is not valid. Bohr model is valid only for a single electron atom. Note it down. Okay, so the next is in Bohr model. So Bohr model is valid for a single electron atom, means atom having just one electron. So Bohr explanation for hydrogen and hydrogen like atom. So hydrogen like means atoms which have single electrons. So it could be hydrogen, it could be helium plus, it could be lithium 2 plus, lithium 2 plus, or this could be beryllium 3 plus. So Bohr's model is valid for these 4 atoms. It's not valid for any other atom. So hydrogen, helium plus, lithium 2 plus, beryllium 3 plus. Now, Bohr's explanation means using Bohr model, you have to calculate the radius of the orbit. Like you have hydrogen atom, you have to calculate the radius of the first orbit, radius of the third orbit, velocity of electrons in different orbits, then time period and frequency of electrons in different orbits, energy of electrons in different orbits. So here that you need not to do the entire derivation. Derivation is not required. Just memorize the relations. There are few questions in which you need to use some steps of derivation, but that will those numericals we'll discuss in class. Just note it down, then we'll see Bohr's model. So remember, you can't apply Bohr's model for carbon. You can't apply Bohr's model for nitrogen because they have more than one electron. But you can apply it for hydrogen, helium, lithium, and beryllium. Explanation means you need radius of orbit, you need velocity of electron in that orbit, you need frequency of electron, you need time period of electron, and you need energy of electron. This is Bohr explanation. You have to calculate all these things for an electron. Okay, time over. Okay, I'll stop here.